The next topic is the centrifugal pump. One of the most common radial flow turbo machine is a centrifugal pump. It has two main components. One is an impeller attached to the rotating shaft. So this is impeller in the green color and attached to the shaft. Okay, and stationary called the casing house or volute. That is the casing. Okay, on the casing housing or volute enclosing impeller. The impeller consists of the number of blades. So that is number of blades. This is number. And you can look at this. This is in other view is blade. And called vane. Okay. As the impeller rotates, fluid is sucked into through the eye. So this is the eye of the pump, and water sucks through this direction. The eye of the casing and the flow radial outward. Okay, one is moved to the eye and moved to radial outward. And this flow is correct to and flow out on this direction. Okay. Energy is added to the fluid by rotating blade, and both pressure and absolute velocity are increased as the fluid flow from the eye to the periphery, okay, of the blade. Two types of impellers shown in the below figure. This is one open impeller, another one is enclosed or shaded impeller. Okay. Theoretical consideration for centrifugal pump. The next figure shows the typical blade passage. Okay, the velocity, the V1. This figure shows this is inflow and this is outflow. Okay, this have the absolute pressure V1. This is V1 of the fluid flow entering the passage is the vector sum of the vector of the blade. This U1 is the blade velocity. Okay, and the V1 is the relative velocity or the velocity that have been seen from the observer on the blade. So we can write typical equation for V1 equal to W1 plus this equation for entering the pump, and the other end is the same. There is a V2, U2, and W2. You can write the same equation. Okay, so we move back to equation. So that is equation of the V1, V2. Okay, and for the math flow rate is the same. So we can write the T sharp based on this equation and substitute m dot in this equation. And v theta 1 and v theta 2 is tangential component of the absolute velocity v1 and v2. Okay. For the power transfer is given by the T sharp times the angular velocity. Okay. So we have combine omega times the T equation of T sharp, and for U1 is equal to R1 times omega and U2 R2 times omega. So we obtain this equation is the power of the pump in unit is watt. Okay, and for the shaft power per shaft power per unit mass, we can derive equation 8 by mass. So we got this equation m small m dot shaft in equation 9. Okay, and this we write the equation for the pump. The power of the pump is equal to different pressure between head out and head in, and plus the loss into this equation 10, and equation 9 and 10 is equal to and divided by G. So we got equation 11. Okay, and for the ideal rise, head loss is 0, and uh, HI is ideal head rise is equal to H out subtract H in. So we got the equation 12. Okay, for the head rise of from the pump. In case of fluid has no tangential component of velocity, so normally V theta 1 is 0 as it enter the impeller. So the angle between the absolute velocity and tangential velocity is 90 degrees. So from equation 12 to equation 13, okay, we have V theta 1 is 0. Okay. And next, what is the V theta 2 in this equation? So we can derive from the velocity vector at the out. So in this case, if we write equation for this triangle, okay, so we can write that the cos beta 2 equal to the difference of u2 is here, u2 subtract v theta 2 subtract v theta 2 divided by vr2, that is the in the middle of vr2. Okay, so next, so we can rearrange to get v theta 2 and substitute in equation 13, substitute in here. So we got equation 14 is a cos beta 2. Okay, and the next, we can write the q is equal to pi r b vr2, and we can find equation for vr2 and substitute vr2 in the equation 15. So we substitute vr2 in here. So we got this equation for head rise for equation 15. And finally we got this equation 16, head rise for the pump. Okay, and for inflow, normally v theta 1 is 0, so it means alpha is 90 degrees. We assume that there is only the velocity perpendicular to the surface, not the tangent. Okay, so if we plot the curve from equation 16, so we normally we have equation head right is the reverse proportion to q. So in this one, if we write equation for example, so for any flow rate, the heads start from the initial or ideal heads, and there's a friction loss, and there's another loss. Okay, the head loss, actual loss is smaller. Okay, compared to the ideal loss. And this figure show the typical performance curve or characteristic curve for the centrifugal pump. This figure show the head flow rate is a function of head, brake horsepower, or power and efficiency. For this kind of the curve, we have done in the hydraulic lab to draw this curve in the same graph. Okay, already practiced in the hydraulic lab. And the last thing, that power scaling. Okay, so in this case, if we change the angular velocity, the flow rate is changed. Okay, it's a direct proportion q1 and q2 is a proportion to angular velocity. But for the head is the power of the angular velocity, and for the power is q of the angular velocity. In case of we change the angular velocity for and find q head and power.